You're navigating a maze with no map. You pick a path, go deep, hit a wall. Do you explore that dead end to the absolute end? No. You recognize it's hopeless. Backtrack instantly, try another path. So why do computers exploring search trees sometimes waste time in dead ends when you instantly know to give up? What's the difference? Let's think about how you explore when you're lost. You're in a building, searching for room 305. You turn down a hallway. You check rooms, 101, 102, 103. You realize all rooms are in the 100s. Room 305 is on another floor. Do you check every room? No. You recognize the room numbers here are too low. 305 is definitely not on this floor. You backtrack and try the stairs. You're not exploring blindly. You're pruning, eliminating branches that provably can't contain what you're looking for. This is the power of backtracking with pruning. Not just undo and try next thing. Actively recognize hopeless branches and skip them. When you prune, the search space shrinks catastrophically. Instead of exploring a branch with millions of nodes, you eliminate it in constant time. But here's the puzzle. How do you know a branch is hopeless without exploring it? You need a heuristic, a fast check that says nothing good can come from this direction. Backtracking is basic. Try a move, if stuck, undo and try another. But without pruning, it's slow. Example, solving a puzzle, like sliding tiles or Rubik's Cube. Blind backtracking. Try 1,000 moves, get stuck, undo last 100, try different variants, repeat. You explore millions of nodes. Most lead nowhere. Better, prune. Check each move before making it. If I do this, can I possibly reach the goal? If the answer is clearly no, by some fast heuristic, skip this move entirely. Suddenly, you explore 100 nodes instead of millions. How? Heuristics. For Rubik's Cube, corners are separated from target, minimum 2 moves needed. If we've already used 10 moves and corners still separated, skip this branch. For pathfinding, direct distance to goal is 50 meters. I've traveled 200 meters and still 40 meters away. Prune this path. Designing good heuristics is an art and science. The best heuristics are admissible, never overestimate, and consistent. Obey the triangle inequality. Here's how intelligent backtracking works. Piece 1. Complete search without pruning. Depth-first search with backtracking starts by picking a branch. It works, but explores huge spaces. Piece 2. Bounding. Before going deep on a branch, ask, can this possibly lead to a good solution? Current best path, 200 meters. Current branch, traveled 150 meters. Direct distance, 100 meters. Best possible, 250 meters. This is worse than current best. Prune this branch. Example, chess. Current best evaluation, +5. Current branch. Best I can achieve is +3. This is worse than alternatives. Opponent won't do this. Prune. Piece 3. Branch and bound algorithm. Compare to blind backtracking. The if child cost less best cost check is the pruning. It eliminates branches. Piece 4. Heuristic search, A*. Even better, use a heuristic to estimate remaining cost. A* prunes based on estimates. F of node equals current cost plus heuristic. Traveling salesman. If we've visited 8 cities with 500-meter distance, and best found so far is 550 meters, prune this branch. Result, solves in seconds instead of hours. Pruning works only if your bounding heuristic is tight. Loose bounds prune nothing. Wrong bounds skip optimal solutions. Prune too aggressively, no longer correct. Remember the original question? Why do you instantly know to backtrack? You have pruning intuition. Computers can do the same if you give them bounds. Exponential search becomes tractable with pruning. Without, 1 million nodes explored. With good pruning, explore 1,000 nodes. This is not a small speedup. When you face a large search space, find a bounding function, use it to prune, and refine the bound. Better bounds prune more. The difference between search that scales and search that doesn't is pruning. When you recognize a dead end, you don't explore it, and neither should your algorithms.